Today, I want to talk about bonding in um, complexes of transition metals. You may be familiar with valence bond theory from Chemistry 1A. There are some limitations to this if we try to apply it to bonding with transition metals. So we'll kind of leave that aside for now and introduce this new uh, way of looking at bonding that you haven't seen before. So just be aware there are reasons why we're doing this, so it doesn't explain the colors we'll be talking about or some of the magnetic properties very well. One thing we do know for sure is the geometries of these complex ions. So these are all geometries you should be somewhat familiar with from Chemistry 1A. So we have the linear geometry, tetrahedral, square planar, and octahedral. Don't worry about hybridization. We're not really going to be focusing on that at all as we discuss this, but just remember what these shapes look like. We'll be focusing mostly on the octahedral shape for this course as we apply this to complex ions. Although there are complex ions that will fit with some of these other ones as well. So how we are going to explain bonding in complex ions is with a model called the crystal field theory. So a few things related to this in terms of why we're doing this. First of all, we have to understand again that transition metals can form multiple types of charges. They can do lots of things here. So we can't predict their charge the same way that we do with representative elements. So those are just kind of some of the basic background things we need to know before we introduce this theory. And that will end up relating to essentially, as we've discussed earlier, what's going on with the d electrons. Okay, so let's go ahead and talk about crystal field splitting a little bit. So what we're showing here is we're showing the d orbital. So you might remember from Chemistry 1A talking about what the d orbitals look like. So if you don't remember, we're showing them here. So we have 5 different d orbitals to hold up to 10 electrons. So we have, let's talk about these ones first. We have the 4-lobed ones down here. We actually have 4 that have 4 lobes, and we're showing kind of their orientation where they're kind of in this axis where they're not quite aligned with what we're showing as where the ligands will be, as we'll see. And this one, and in this one. And we're just basically turning this 90 degrees one way and then 90 degrees the other way to get from one to the other for these 3. This one fits kind of in the same plane as this one, but again, we're changing the orientation by 45 degrees there. That ends up aligning it with the location of the ligands. So we can think of these 3 as being similar in, based on what we see in Chem 1A in terms of their shapes. But this one is different in that it is aligning directly with the ligand locations, whereas these ones down here are not. They're offset from the ligand locations. The dz squared is also aligning with the ligand locations. So what we see is where if we have just the metal by itself, these 5 are identical in terms of their energy. However, as soon as we start putting bonds to that, those bonds will occur in certain locations. And if those locations are different in terms of their proximity to an orbital that may or may not have electrons, what that does is it makes a difference between those. So hopefully you can see that for the 3 down here, they're kind of away from the ligand location. So you can have electrons that are not basically right on top of those ligands, whereas for the 2 up here, they are not. They are basically on top of the ligand location. And that affects what we call crystal field splitting. And we'll see what that looks like. So this is basically saying what we had just talked about. So crystal field splitting is based on repulsions between electron pairs in the ligands. So the ligands have electron pairs. That's why they are stabilizing these transition metal complexes, and any electrons present in the d orbitals. So if there are electrons present, there will be an increased energy there, and maybe there aren't electrons present there because of that increased energy. And so we'll see how we end up accounting for this. The other ones, so the ones we're showing again at the bottom, do not lie on the same location as the ligands. Their nodes are, node being again where you don't have electrons, are at the ligand locations. So because of that, the repulsion is less for these three than it is for these two. Okay, so this is what ends up happening. We have a splitting occurring for the d orbital energy levels. So over here we're showing in a free atom, they have lower energy overall because you don't have other electrons trying to be in that same space. And then when you start adding ligands, that energy goes up for all of the electrons. So we see they're all higher energy. However, they don't go up equally. So these x, y, y, z, x, z orbitals where you are not aligned directly with the ligand location go up a little bit. And then the z squared, x squared minus y squared go up a bit more because of that, what we call splitting of the d orbitals. Okay, so there's this splitting is the difference in this delta symbol we're using to show that splitting, and it's the difference in energy between the three that are lower energy and the two that are higher energy. The value of that delta depends on a lot of things, and so some of what we'll be looking at is what can affect that. So it could be based on the kind of ligand, so it could vary depending on the type of ligand you have. Could vary depending on the type of metal ion, its oxidation state. Lots of things affect that value, and as that value changes, we get different possibilities, as we'll see. One of the reasons we might care about this is that that splitting, that's whatever that delta is, it's usually pretty small, is responsible for some of the colors we will see with these kind of complex ions. You've actually seen some of these already in the lab practical. So when you, or well, potentially depending on which unknowns you have, you could have added something to see a bright color. Those intense colors are because of that delta. So what's happening is you can have electrons jumping from the one of the lower three up to the upper two. And when they do that, that energy gap is small enough that it is associated with visible light as opposed to, UV light for kind of the typical jumps between electron levels. So that's why some of these have these really intense colors, is because of that gap there in the complex ions. Okay, one other thing I want to remind us of, when we make an observation of a color, what we're seeing is the complementary color of what is being absorbed. So if we are looking at this particular solution that has a purplish color, what's happening is that we're seeing what was not absorbed. So the solution itself, we can see here, is absorbing in kind of this blue and green and yellow areas. And by absorbing here, we see the colors that are not absorbed when we look at that. Okay, so just a reminder of that's what's going on. We're observing the color of the opposite of what is being absorbed. So again, these colors that we see in complex ions are due to the transitions between those split d-level sublevel orbitals that we called delta earlier. And we could find that wavelength. So thinking back to chemistry 1A, how you did that was with this equation. We're not going to focus too much on doing that calculation for this course, but that's how we could find out exactly what that is. Okay, so I mentioned a lot of things can affect the strength of these fields, and one of those is the ligands. So the size of that energy gap will depend on the ligand that is attached to the metal. And we're not going to be able to get into all the details of why that is in this course. But we have some ligands we call strong field and some we call weak field. So strong field means that they have a stronger bond. Weak field means they have a weaker bond. So you can see some of the strong field ones up here. Cyanide, nitrite. This is, I believe this is ethylene diamine and ammonia. Okay, so these are stronger ones. Weaker ligands like water, hydroxide, any of the halide ions. So these are differences in terms of the strength of the ligand, how strong the ligand binds to the metal ion will determine some of the things in terms of how they end up forming these complexes. The size of the gap will also depend on the type of metal ion. So the gap will increase as the charge increases. Metals with large charges will have larger gaps. Metals with smaller charges, so +2, will have lower gaps. And it also sometimes depends on the specific metal ion. So we're showing the trend here. I'm not going to care that you remember the difference between cobalt and chromium, for example, but just know that the +3s are going to generally be bigger than the +2s. Okay, so again, these are determining how big that gap is, that what we call delta. Okay, so some of the properties caused by this, first of all, we have magnetic properties. So because of that gap that we call delta, we can have different electron configurations, as we'll see. So the strength of the crystal field will determine the electron configuration in terms of, do we put all of the electrons on the bottom 3, or do some of them go on the top as well? So it depends on the size of the gap. If we have a weak field, the 4th and 5th electrons will go into the higher energy dz squared and dx squared minus y squared orbitals. So that is if we have a weak field. So if the gap between them is fairly small. What that does is that gives us a lot of unpaired electrons. Unpaired electrons give us a paramagnetic complex. If we have a strong field, what that means is that gap is bigger, so it's less energy to pair those electrons up than to push them up to the top 2. So for if you have between 4 and 6 electrons, they will end up pairing up in the dxy, dyz, and dxz orbitals on the bottom and leave those top 2 orbitals completely unfilled. So this happens if you have a strong field with a large gap, then everything goes to the bottom. So you end up with all of the electrons are paired, and the complex is only diamagnetic. It is not also paramagnetic. So here we're showing some examples of that. We're showing something with a small gap and something with a large gap. One thing we haven't used this term before, low spin and high spin, are other ways of talking about the same thing. So high spin means that you have electrons in up here where you still have some unpaired on the bottom. Low spin means they're all on the bottom, so they're all paired up. We don't go to the top, go to the higher energy level until the lower energy level is sublevels are filled. It might sound a little bit backwards, but a small gap corresponds to high spin complex. A large gap corresponds to low spin complex. So we're seeing here these electron configurations. So we'll look at an example in a bit of how we get to this. We can talk about it right now. So we have we would look at the periodic table. We would look up iron. We would see how many electrons it has from the periodic table, and then how many it has in the D section. So actually, let's go ahead and do that. Okay, so here we are seeing the periodic table. We see iron has 6 D electrons, so you should be able to find that from any periodic table just by counting across 1, 2, 3, 4, 5, 6. And we saw an example of this earlier. So let's go back to what we're looking at here. So iron has plus 6, or has 6 D electrons, and we have a plus 2 charge. The plus 2, we're losing the S electrons, right? We lose the S first, so we haven't lost any of those D electrons yet. So we have 6 electrons. So we have 1, 2, 3, 4, 5, 6. Okay, so we because we have a small gap, we put them in the top before we come back and put so the 5 one at a time before we come back and put the last one pairing it up. Okay. So with a small energy gap, we go to the higher ones before we pair up the bottom ones. However, here we have something that has, so the difference between these, this is a weak field ligand, this is a strong field ligand. Let's go ahead and talk a little bit about how many electrons we have here. So we have here we had a plus 2, here we have a minus 4. Well, remember cyanide has a minus 1 charge. So if we have 6 minus 1 charges, that and we end up with a minus 4 overall, that meant the iron was a plus 2. So it's the same charge of iron from here to here. We'll look at an example later where we go through this a bit more. But essentially, because we have a large split here, all of these go on the bottom. Okay, so 1, 2, 3, 4, 5, 6. So that's how we add those up. So high spin complex is a small difference in energy. Low spin complex is when we have a big difference in the energy. When we have high spin complexes, we often have paramagnetism because we have more places where we're putting electrons before we pair them up. With low spin, we often have diamagnetism. It turns out that the only time this matters, this doesn't matter for every single time we have a complex. It only matters with electron configurations that end in D4, D5, D6, or D7. If you only have 3 electrons, they're going to go on the bottom regardless of what this difference is. And if you have 7 or more, then you already are in the point of having all of these filled as well as some up here. So at that point, it doesn't matter low spin or high spin because they'll be the same either way. Okay, I want to go ahead and look at an example. So go ahead and maybe pause your recording and try to do this. And then we'll come back and discuss it together. Okay, so let's go ahead and solve this problem. So first thing we do is we recognize we have chromium. And so for chromium, I'm not going to pull up the periodic table now, but you can look at the periodic table yourself and see that it is a D4. Okay, so that's how many electrons it starts with in terms of its D electrons. And then we want to look at, well, how many electrons does it have here? Has it lost some of those already based on the complex ion we have? So in order to do that, we recognize that for cyanide, we have a -1 charge. So we have, if we want to balance this out, we have whatever the charge is for chromium. We have 6 cyanide ions, -1 charge for each of those. And the whole thing has a -4 charge. Okay, so that's what we have. Whatever we have for chromium, minus 6 equals a minus 4. So if we do the math there, we see that chromium is going to have a plus 2 charge. So the chromium is going to lose 2 electrons from its starting amount. So the first 2 it loses are the s electrons. So it doesn't actually lose any of the d. So it is still going to be a d4 in this case, because it lost the s electrons first. Okay, so we'll go ahead and write that down. So we start with a d4, okay? So let's go ahead and write our electron configuration. So it is octahedral, we know, because there's 6 of them. Also, we're only doing octahedral for this course, so you'll always have the same splitting pattern, and it's just a matter of figuring out how many electrons you have there, and then where do they go. So we have 4 electrons, so we have 1, 2, 3, and then we have to decide where to put the 4th electron. Does the 4th electron go down here? Does it pair up? Or does it want to be by itself? And to decide that, we have to decide how big that gap is. Is that a small gap or is that a big gap? So the few things we have to base that on, we look at the charge. It's a plus 2 charge. That's not a big charge. So that's probably not going to determine whether that's big or small. The other thing we have is that we have a cyanide ion. Cyanide is strong. It is a strong ligand. So it's going to make this gap large. Okay, the gap is large because we have a strong ligand. Because the gap is large, that electron is going to go right there. So that is the electron configuration for this complex ion. Okay, I want to end by talking about a couple of applications of these coordination compounds. So we can these complex ion coordinations compounds are used in the extractions of metals from ores. So cyanide complexes are used for silver and gold. We can see nickel there with carbon monoxide. So these are ways of extracting metals. They're also used as chelating agents when we have heavy metal poisoning. So the idea there is if you have a very strong ligand, it can bind up any heavy metals that are in someone's body. So EDTA is often used for lead poisoning, for example. Also for qualitative analysis, which we all have a little bit of experience with already from the lab practical. So we have some of these bright, obvious colors that show up in the lab, again, depending on which unknown you had, that are telling us, yes, I have this particular metal ion when I see this particular color. So potentially cobalt and iron, we can see here with the thiocyanate ion have very specific colors. There are some ligands that do prefer specific metal ions. So again, additional things that go into this sort of qualitative analysis. And then also, because of these very bright colors, there are many dyes and things where a color is necessary that are based on transition metals in these complex compounds. There used to be even more of these used, but we now know that some of those metals are toxic, so we avoid using them. Lead paint, for example, has been used in the past. We don't use that anymore. But other metals that are more safe are still sometimes used in this way. I want to end with biomolecules as another very important application where we sometimes see transition metal complexes. So there's a list here. I'm not going to read through this, but these are some important transition metals that show up in certain biological functions. and we'll look at a few specific examples. So one thing that is often true for transition metals in biomolecular settings is this porphyrin ring. You don't have to worry about memorizing what this looks like. That is a detail for much later in your academic career, if you so choose to go in that direction. But what I want you to recognize here is that we have these nitrogens that are kind of pointing towards this empty space right here in the middle of this ring. And we can kind of see it over here as well. Those nitrogens are able to bond to a metal in here, and by doing so we get these kinds of coordination compounds. So here we're looking at some examples of where that porphyrin ring shows up. So you probably have heard of hemoglobin as being an important molecule in the blood, and you probably are aware that iron is important in the blood. Well, this is how that works out. So we have this porphyrin ring, and inside of that, those nitrogens are bonded to an iron. We have some of these bonds are kind of chemical bonds. Some of them are sort of an intermolecular force, kind of like not exactly a hydrogen bond, but kind of a weaker bond going on there. And so the iron is basically stuck inside of this molecule, and we see it shows up in 4 places on the hemoglobin. And in terms of the functionality of hemoglobin in the body, in the blood, it's basically these 4 places are where it's doing anything. And what happens there is that the iron is able to bond also to oxygen molecules. And so when we breathe in oxygen, that oxygen bonds to the iron, and then the hemoglobin moves through the bloodstream to a place where there is not as much oxygen, and then it releases that oxygen there. So that's how hemoglobin works as a way of transporting oxygen through the body. Cytochrome C is another important biomolecule. Again, we see kind of the similar porphyrin ring structure there. Chlorophyll also, we see a similar thing there, with magnesium being the central atom in that case. And then another important application in carbonic anhydrase, where here we have zinc. It's a different structure, but we have zinc in the middle there. And it does catalyze some important reactions. So just to summarize the applications here, lots of important biomolecules that work based on having a coordination chemistry with the sort of metal center that often is also bonding to other things as well. And then finally, there are some drugs that are based on this sort of coordination chemistry. So cisplatin is a great example. It has a different coordination than the ones we've looked at already, in terms of it's square planar instead of octahedral, and it doesn't have the big hemoglobin structure around it, but this is an important application as well. So lots of ways in which transition metal chemistry is important in biology. That is it for chapter 25. Please let me know if you have any questions. We will be picking up with chapter 20 when we return.